Assalamu alaikum wa rahmatullah. Um, can everybody hear me clearly?
Yes, Dr. Ahmed.
Yeah.
It's clear.
Okay, thank you.
Thank you.
I'm glad to welcoming everybody here in this platform, and today I'm also glad to share my presentation with my dearest colleague, Dr. Safia Athar from University of York in Canada, and therefore I will start my screen. Just in a minute. Yeah. So, hi again. Before we start, I will have a few words for Dr. Safia in a brief, just to identify Dr. Safia in these words. So, Dr. Safia Ahmed Athar is a researcher from University of York, as I said before. She finished her master's in mathematics in 2014 from University of Guelph. Actually, in 2017, she finished her PhD in mathematics from the same university. Afterward, in 2018, she started her position as a researcher in the Center of Disease Modeling in University of York. And since then, she published 8 publications, and she participated in more than 6 conferences and workshops. Her main research interest focused on the disease modeling and analyzing the disease pandemics. She also participated with the Sanofi company in cooperation, which actually Sanofi company is a big vaccination company in the United States. And her cooperation with this company is for analyzing the influenza vaccination. So I welcome Dr. Safia again, and then we started with our presentation now with the first slide here. As you can see, and from the slide that she also has interest in her research with game theory and decision making and infectious disease. She's currently, as we said, she currently works at the Disease Modeling Center in York University, and her recent work is focused on Ebola and COVID-19 and influenza disease. She actually focused on mixing the disease modeling with the game theory in one focused research, and also she participated in many famous international conferences in the University of Toronto, which is called the industrial problem solving workshops 2019, where actually I participated with her in this conference. So we will talk today about the infectious disease models. Dr. Safia will give us a brief description. Afterward, I will speak a little bit about the game theory and its application, and they will give some examples about that. And we will back again with Dr. Safia. She will show us how the disease models can be coupled with the game theory to study the behavior of publication in the future. So I welcome Dr. Safia again, and I will give her the screen to share her screen now with appreciation. Dr. Safia.
Thank you, Dr. Ahmed. Assalamu alaikum, everyone. I hope all of you are in good health and enjoying the weather in Iraq. As I came to know, it's a very nice weather there. We are in a kind of a spring weather right now in Canada, not very cold, but enjoying anyways. And I hope everyone is safe from this recent virus and staying safe everywhere. So let me share my screen quickly so I can start my presentation. If you have any question, please write in the chat, and I will ask Dr. Ahmed. Please feel free to talk if you have, like, if you want to say something in your own language. I don't completely understand Arabic, but kind of, and I will ask Dr. Ahmed to translate for me if you're comfortable in asking in your own language. So we are open with the language. So let's start. For a moment, I have to close my screen just in case. Okay, leave it. Okay, so let's start what we are talking about. So you have seen the topic. So we are discussing today disease modeling and game theory. So my part in the beginning is to talk about infectious disease modeling. Ahmed already talked about this slide, what we are going to present today. So here comes the very first thing. Infectious disease modeling involve models. So what are they? That's very important to know. A model is a simplified description of a complex entity or a process, you say, okay? It's very complex thing. If we have some complex process and we want to make mathematical equations or representations, here comes your descriptions. So infectious disease modeling, why might we want a model? So the main points we have to keep in our mind to improve our fundamental understanding of how system works and to predict or project how the system will change over time and possibly in response to manipulation. So what we want from, suppose you made a model, and what you want from your model. The very first thing is simplicity. Make your model as simple as you can see. See the simple drawing of a tree, so you can understand what you want. Then realism. Realism comes with a prediction. What you want to predict from your model. That's very important. Your goals must be clear about that. Okay, why do we use models for infectious disease, especially? Why we are dealing with these things? The very important thing is the dynamic of infection diseases are very complex. You have non-linearities. It means if you have a small change in the input, you could have a very large output change. And then you know that infectious diseases have emergent properties. It's different from other models. So what we have as a infectious disease modeling, we have two kinds of models: compartmental models, okay, and then we have metapopulation, individual based, special models, neural networks. Metapopulation is when we are dealing different kind of two population compartments. Then you have heard about the agent based modeling. So all these come under the infectious disease modeling. So let's learn about something more about how we go with the infectious disease modeling. As you see on your screens, this simple epidemic can be divided into four kinds of main models. The number one is SIS model, which is susceptible, infected, and susceptible model. Means if you are not immune with the disease and you are always susceptible, then we make SIS model. Then what is SIR model? It's a susceptible, infected, and recovered. Once you get infected, you recovered and you're immune for the whole life. This is SIR model. Then we want to make some changes in SIR model. Suppose like in the COVID situation, we are looking for vaccination to make ourselves immune. So we add another compartment. So we mostly call it SVIR model, which I'm going to talk about after Ahmed's discussion on game theory. Then there is another model which is called SIR with mutation. Then in the lab, if you're in the lab, what you have to do, you can use any of these models with treatment, long-term behavior with or without treatment, or exploring the parameters with less infectious version. Now I'm talking about this SIS model. We mostly go with a diagram first, and then we model. But it's not necessary. You can go even with the model directly. If you have a grip on the modeling, you can directly write the model. And when you're writing your paper or you want to publish, you can make the diagram. Okay, from the model, what we need to analyze the model. So either we go in this direction, like phase portraits, time is implicit, you can find the equilibrias and stability of equilibrias, or the other thing is solve directly, like mathematical way. Okay, time series equation or the solution over time, which we call as dynamical solutions, like using simulations, producing graphs, and looking at how your population is changing over the time. So I'm talking about today SIR model. Now in SIR model, you can see here, we have three compartments, S, I, and R. S for susceptible. Basically, we all are susceptible at the moment to the COVID. I are those who are infected. Unfortunately, all those who got the virus comes in this compartment. And once you are feeling better, you go to the recovered compartment. Now, do you remember, in this case, the population is divided by healthy or disease status, and it's a kind of prototype, simple model I'm talking about. And also remember, S, I, and R are added up to the total population. Now I'm showing you the equations. Look at here. Now this model is without any demography. The demography means there is no birth or death rate is involved right now in this model. Very simple model. You can see some red things here. Beta I, which is the infection part. Beta is the transmission parameter. And how we define the transmission parameter? We define beta as the transmission probability context time the contact rate. So it means what is the probability of you infecting other sitting close to you. Therefore, we are doing the social distancing and all these virtual conferences. So we can't be in contact of the others and we can't get infected. Gamma is the recovery rate. And my slide is a little bit dim. I don't know you can see properly, but I'm reading for you. Gamma is basically 1 over your duration of time. Duration of disease. Uh, I'm giving an example for this, like the time series for recovery of influenza is around 5 days. So we take gamma as 1 over 5. Or some people have some different persons have like 7 days, 8 days. The maximum limit for the influenza is from 5 to 8 days in the literature. Like for the COVID right now, we are having 14 days recovery period. So the gamma or recovery rate in this case is 1 over 14. Now this system is closed. Closed means if you add up the three compartments, you will get the total population. So there is no birth or death involved in it. Then comes basic reproduction number, which is very important to see whether your epidemic will occur or not. Now, what is this basic reproduction number? It's basically the expected number of secondary cases of the disease produced directly by an average infectious individual entering an entirely susceptible population. What does it mean? For those who don't understand what does the reproduction number means, if the whole population is susceptible and I just introduce one infection case, so the expected number of secondary cases you will produce, like if suppose I'm infected and I come into contact with 1 or 2 persons. So how could I infect those persons? The number of secondary cases I can produce, maybe 2, maybe 4, and so on, are shown by the basic reproduction number. Then there is very important thing. When this reproduction number, basic reproduction number I'm talking about, is greater than 1, then your epidemic occurs. If it's less than 1, then it's die out. So we try, at the moment we are trying to reduce this reproduction number less than 1, and you have seen in the news, if you read the different articles about happening, whatever the happening in COVID in different countries, everybody is trying to reduce this basic reproduction number less than 1. So we can develop the immunity in the community and we can control the spread of disease. Now, what does R naught depends on? That's very important. Transmission probability per contact times contact rates times the duration of infectious period. Now, basic case is the random mixing and no heterogeneity. We are just taking the random mixing of the population and not like different cases. It's very simple one right now. Otherwise, we will calculate. Suppose we introduce the vaccination in the population. In that case, this R naught has a different value. Then that R naught or the reproduction number is called effective reproduction number, because now you're in the vaccination is also involved in your population. So here is a simple demographic curves. You can see that S is represented by this light green or yellowish line, if you can see on your screens. So we have taken the whole population as susceptible. So you can see the whole population, the susceptibles are decreasing over the time. Red is shown as a bell curve, which is infection. So the infection arises over the time and then it start decreasing. And the same thing, your recovered people are, your recovered population is increasing and then it's come to stability. This is a very basic SIR model. Now it will change when we introduce the demography. Demography means when the birth and death rate is involved. So here is the model with the demography. Now see, if you see susceptible, the arrow coming in represents the births and the arrow going out of each compartment represents your death rates. So it's the same kind of model, except now I'm taking birth over SINR. All are in susceptible. Then infection, this red part is infection going out into infected. And then there is mu S. The mu is representing both fertility and the mortality at a time. We use the same parameter just for simplicity. It doesn't matter, you can change different, mostly the deaths are represented by D, and this mu is represented by lambda in some of the cases. So it's up to you. You can use any parameter, but you'd have to define your parameters accordingly. Then you can see I compartment, the infection coming in, they are recovering, and there is a death rate going out. And then in the R, all infected are recovered, and still there is a possibility of death in the recovered. This is also a fixed population. Now the question arises here, how can I check the population is fixed? The very simple thing, add up the 3 equations, these 3 ODEs. If you get your answer equals to 0, it means your population is preserved. Here is the demographic curve with the SIR model. Now you can see the susceptibles are decreasing, but since there is an inflow, so the susceptibles increases over time, then there is a, you can see the dip, then again going increase and decrease over the time. Your infection is the same curve, but as your susceptible increase, there is more infection coming on. So there is not only one peak, but there are multiple peaks in this case. Like in the COVID, you can see there is one wave and there is another second wave occurring right now, unless we introduce some vaccination. And the same is case with the recovered. As you can see, susceptible increasing, it means the recovered are decreasing. And after some time, we see the rise in the infection curve and so on. And then this goes on. So after SIS, this one is susceptible infectious, SI model. This is another example. We mostly use SI model for the diseases where there is a, less chances of getting immune. Like you can say that influenza, you're not always immune for the influenza. You're always susceptible. Even if you're recovered, you can get the infection if you're not vaccinated. Then there is another one which I have like susceptible, exposed, infectious, and recovered. Now, many of you are thinking, what is the point of using exposed? When you are susceptible, you get in contact with someone with an infection, but your symptoms are not visible. So let's talk about COVID right now. I don't know, I get exposed to someone. I went outside, I may come in contact with someone with the COVID symptoms, and I don't know that I'm exposed because there is no symptoms showing on right now. I move to infectious compartment only when my symptoms, onset symptoms are visible. And after that, like passing 14 days or some medications, or God forbid if I have to go to ICU, then I come to the recovered compartment. That's simple real life examples, what we are dealing with right now. So I will stop here and I ask uh, Dr. Ahmed to carry on with his part, and then I will come back to explain more about um, example, which I'm working right now.
Thank you, Dr. Safia. So I'm going back to share my screen now, but in just a few seconds, yeah. So as Dr. Safia explained before, so we are trying actually to merge the two concepts that we are discussing about SIR model with the game theory. Therefore, we are actually need to understand the basic concepts here. So as we can see here, there is the main definition of game theory here, which is defined as a mathematical model of interactions with various players that are making decision over time, which means most people, most players here in the game are human being or people in most case scenarios, I mean. So to understand that, let's see what we have
Let's
here.
assume Sarah promises to give Matt $100 if he runs a mile in less than 7 minutes. In this case, everything depends on Matt. He can train until he consistently succeeds, and when he's ready, he can show Sarah and get his $100. Game theory doesn't study situations like this one. Instead, it studies situations involving more than one participant and in which not everything depends on one person. For example, in the game of chess, the other player's moves continuously influence your strategy. That would be one example of a situation studied by game theory, but don't make the mistake of assuming only actual games are studied. Game theory is also used to, for example, analyze situations in which multiple companies are competing against one another. Just like in a game of chess, the actions of one company are influenced by the actions of the other participants. For example, if a competitor lowers the price, the other companies might be forced to do the same. As you can see, game theory basically analyzes the behavior of two or more participants in situations involving rewards or punishments. The rules of the so-called game are known by everyone, and it is assumed that all players are rational. Now, of course, game theory will never be able to predict human behavior with 100% accuracy. In one situation or another, you might very well do the exact opposite of what game theory suggests, but still, it offers some truly fascinating human behavior insight.
So after this short video, we just introduced the basic definition of game theory. So here I'm trying to to give just a point of view of what is the game theory and what it depends on and what we need to understand the game theory. So the game theory is actually a decision-making science. So what is the decision-making principle depends on? It actually depends on some players, and also these players need some strategies, and also after the players uses their strategies, then they will get some rewards, or we call it payoff, or sometimes they call it utility, also utility function. So the players usually has to be people who make a rational decision, and strategies is actually is a plan that can players use in the game, and the payoff payoffs actually is a rewards that can players gain from the playing their strategies. Here we can just in brief word, we can just talk about few kinds or few types of game, like cooperative games, where in this kind of game where people actually cooperate to share some prize together, and there is no a winner or loser in this game. Just all of them will gain the benefits. And non-cooperative games, which is widely used here in economics and in biology and different branch of science, and it's widely used, which is non-cooperative games. Here we have two players or more. They play against each other and they compete against each other to get their payoffs. Simultaneous games, here we are talking about the simultaneous games, where here in this kind of game where players are playing against each other without any preparation. I mean, it's without any thinking. They just play without thinking, like the rock, paper, scissors game. Sequential game here is actually used widely here in chess games, where every player can know about his opponent's strategies and planning, and accordingly he plays against his opponent according this perspective. Extensive games also is very close to the sequential games, is known is very widely known in economics. And also what we are interested in here in normal games here, normal form games, where we have two players or more can play against each other, and their payoffs is actually a matrix where the payoffs are. Also, there is a zero-sum game and non-zero-sum game. Sometimes it's called constant sum game. Also, we have some games which is called symmetric games, where players have the same set of strategies and same functions of payoffs. And also there is asymmetric game, which is the converse of this symmetric game. So this is the most important types we need to understand here. Anyone can Google every one of these games, and he can simply understand the basics of these games. Here is the most important examples that is known in this field, where we can present prisoner's dilemma. Here, this first game, where we have it's very famous game that's widely used and published and accordingly is actually in 50s of 1950s. It's very famous when we have two prisoners. They put them in different. They try to rob a bank, and then they try the officers put them in different room, and then they have different investigations with them. According this, they have the investigation is going to be like in this matrix where the players have two strategies, either to confess or to defect. So in this case, if both players choose to confess, then we have just 1 year in jail. If one of them choose to confess and the other choose to defect, then the one of them will get about 10 years in prison and the other not. And if also if the other one is choose to defect and the first one choose to confess, then they will get the same amount of year in prison. And if both of them are choose to defect, they will get about 5 years in prison. So this kind of game is known as a normal form game, which is widely used here in which is important. We will use it here in disease modeling also. Another example here I'm talking about is the zero-sum game, which here we have a very famous also game which known as rock, paper, scissors. As you can see, if player one plays rock and the other and player two play also rock, then the sum of the payoff is equal to 0. Here the same thing. If player one use rock strategy and player two use paper strategy, then player one will get 1, means he won the game, and the other will get -1, where the sum is equal to 0, and so on. The last example here, which is the chess game, where we have every player have well-known information about the strategy that his opponent is going to use in the game. So this is basic examples of games that we need to know in our presentation here. Also, there is very important concept we need to talk about, which is the Nash equilibrium and evolutionary stable strategy, the ESS. So the Nash equilibrium, or NE, is a very important concept that is given by John Nash. I think everyone knows this guy from the Hollywood movie that's played by Russell Crowe, which is known as The Beautiful Mind. So it's very, very famous from this. So what is the Nash equilibrium? It's actually a solution for the game where everyone in the game, all the players will be as happy, which is in simple words, in mathematical word, we can say it's an optimal outcome of game where players can't deviate from their played strategy because it's represent the best choice in the game. So this is very important for using the solution or trying to think about the solution of any game. So if we want to play any game for many time, and we have a population that it has to use this game over and over, so we need to think about the evolutionary stable strategy, which is the strategy that will be valid for over time, which is mean that the people always will use this strategy. Here is a very simple example where we have a hawks and doves game, where we can see the ESS, or evolutionary stable strategy, is defined here in simple way. So also we need to know something important here about the game if we are trying to playing this game with a population. So we need to know the concept of replicator dynamics. So the replicator dynamics actually is defined or used when we have a population here, and then we go inside the game and we play the game, and then we have some some selection of population and replicator dynamic, and then we go back to give this information again to the population to play over and over. This is actually defined here in this ODE system here, as shown here in this example, or this equation, sorry. After we know all these concepts, we can see some specific example here, which is known as here in one of my paper, which is known as vaccination game. So let me give you some simple idea here. In busy cities, people are more exposed to various kinds of disease, as we know, like measles, mumps, or polio. So our population, just like Dr. Safia mentioned before, is divided into two subgroups, which is the susceptibles, which represent the majority of the population, and the infected people, which is represent a small group of population. And then we have some individuals who get infected will get some contact rate with some healthy individuals, and this will make the healthy one will get the infection. So the idea of the vaccination game here, if we have a vaccine, we want to introduce it to the population, then how many of these people will accept the vaccine? Because there is some problems here. As you know, people have their decisions, their own decisions to accept the vaccine or not. Because why that? Because some people have some problems against, some fears against the vaccine, or they have some allergies, so they don't accept the vaccine. This is the probability of introducing the vaccine. So here's the game comes here in this part. So either the player will get the vaccine or he will refuse the vaccine. According to this idea, we have this game. We defined a two-player game where each player have the same strategy, either to vaccinate or not to vaccinate. We call it V and NV. And each player, actually this game is called biometrics payoff game, which means each player has different payoffs from the other. We put this comma between them to explain that. So we define this. I here is the income of player one, while C1 here is the cost, perceived cost. And we call it perceived cost here, which means that it's general cost. It's not very, it's only cash or money cost. It's the cost that probably you pay it when you get the vaccine. So maybe you will pay money, and sometimes you will pay from your health. Maybe you get some allergies, or sometimes when you get the vaccine, you get some fever or something like that. So it's a general cost mean. Also here, when in this scenario here, when both players choose to not to vaccinate, then we have here the Q. We define Q here is the probability of getting infection. And when you get the infection, also you will lose something. So you will lose some. You will also lose some health issues from that. As we have it here in COVID-19, some people they get the symptoms, and some people they get heavy symptoms, and then we have some other problems like heart problems or kidneys problems. So this is the lose I'm talking about. So each player will have the same difference, cost, and lose. So according to this game, so we solved this kind of game to get the equilibria, or sometimes here in Iraq we call it the fixed points. So as you can see here, we have in this figure here, we have three equilibria. Two of them on this field, or two of them are we call it pure strategy, and one of them, which is this one, we call it mixed strategy. Okay, so this is the mixed strategy. Sorry. Yep. So I'm finished here, and I will come back to go back to Dr. Safia to finish her presentation. Yeah, can you hear me, Dr. Safia, now?
Yeah, I can hear you perfectly.
Yeah, sorry for the noise.
No, it's okay. I was requesting other participant, please close your mic so it's easy for all of us.
I just muted from here. I am just mute.
Okay.
Yeah,
Okay.
everyone here.
So
okay.
Let me share my screen.
Now you go back to your screen here. Yeah.
Okay, so I need to talk a little bit. Oh, I have to go back quickly.
Yeah.
So why we use maths to solve the real problems? Now remember, the infectious diseases are basically biological problems. Now there are ways to convert a biological problem into mathematical model, analyze it, and then find some mathematical conclusion, and then we convert this mathematical conclusion into biological conclusion. Now it's other ways around. We can even do biological problem by comparing the data and then come up to some biological conclusion, or other way around it happens. So why I'm showing this? Because I'm showing you the work we recently did, me and Ahmed, under the Sanofi problem workshop, where we quantify the annual incidence, which is the annual rate of increase of disease, and estimation of seasonal influenza. We used already collected data for the year 2011 and 12, and then we come up with some incidents and how we can quantify the underestimation in the represented data. So there's something new what we did recently, is already published. So I go back to my example, what Ahmed already explained. Now I'm showing you what we are doing these days. So my example is disease modeling coupled with evolutionary equations. Now for your interest, I want to tell you evolutionary equations are replicator equations, which Ahmed just talk about, but they are time dependent. It's the same kind of equations, but they are time dependent. It's not we are looking for only one time step solution, but it evolves as the disease evolves. So my work right now is to study the individual's behavior under the mass media effect during a pandemic. So here is my recent model. You can see this is SVEIR model. But I divided my susceptible compartment into two subcompartments, and same is the vaccinated compartments. And why I have divided? The S1 is a susceptible compartment like all other disease models, and S2 are still susceptible, but these are those people who don't want to vaccinate. You know, there are always two kind of population. They go for vaccination or they adhere the vaccination. So S2 are those who don't want to vaccinate but want to isolate themselves. Then V1 is the compartment with the part of population vaccinated. So what is V2? V2 are those people who are afraid of the efficacy of the vaccine, and they're afraid of the pandemic, and they want to separate themselves from others and they isolate. Then there is exposed compartment. Since the vaccination in this model, and I just want to mention this is the model for flu vaccine. It's not for COVID or not any other disease we are talking about. This model is for the H1N1 pandemic for 2009. We are using the data from the 2009 to see the behavior of the population. So vaccine in that particular year 2009 is 62% efficient. So it's not covering the disease like 100% coverage. Therefore we put the chance of getting infection in the vaccinated compartment, so they can get infected at some reduced rate, epsilon beta, and they can move to the exposed compartment and may get infectious and then recover. And here you can see M. M is the mass media effect, which we want to study how the mass media uh, affects, changes the behavior of the population. So mass media is the news is coming about the pandemic in your newspapers or maybe on some written articles, but you can always use this media as a social media also. The data I'm using is the mass media, like the English and French newspapers articles, what are reported at that particular time. So mass media is another equation which is working on the top of this model. So my output was to decrease the infection in the population in both cases, either they are isolating, social distancing, or the vaccination. So here are some results which are, because this process is still going on, these are not final results. I'm just showing you some basic results of my work. So the first graph on the left-hand side is the susceptible population, and on the right-hand side is the vaccinated population. So my population for S1 is with the red lines, and for S2, which is 0, at the start of the disease, nobody is isolated. All are in S1 compartment. It's like we all are susceptibles. Then there is a model, which is the replicator model, as shown by Dr. Ahmed. The same kind of model is working coupled with this disease model. And because of this behavior change, the people are deciding to move to the isolation. So you can see here, my peak is emerging at 50 days. So as the peak emerges, the people who don't want to vaccinate, they move to S2 compartment. Okay, what's happening in the vaccination compartment? We want to see that also. So my 42% of the population was vaccinated, almost 42%, because I'm using the data of 2009. So 42% of the population at that particular time was vaccinated. So, and this data is for North America. So it's not for the whole world. So don't worry about that. So this is the change in the vaccination. It means we started with around 4,200 vaccinators, but vaccination is increasing over the time, and you can see small jumps in it. And at the same time, you can see some of the people are got afraid of the efficacy of the vaccine. So they move to the isolation, though they are vaccinated, but they prefer to isolation. And we can see an increase in the isolation. Now, if you look at the graph very carefully, as I told you, my peak of infection is around 50 days. So we see the increase are after 50 days, almost starting before 50 days, but it keep on increasing and then it start decreasing as my peak decreases for the infection, which makes sense because once the peak is passed, the people are comfortable. And since there is a waning behavior also working, so people get like a bit carefree, like it's happening in COVID. So people want to go out, want to enjoy with their families and friends. The same is here happening. So these are the replicator strategies. And you can see how the strategies are involving, since, as Ahmed told you, these are the biometrics. So X1, Y1, X2, Y2 are the two strategies which are working together. So X1 is player 1, Y1 is player 2. And this is how they are changing their behaviors accordingly with the peak and with the passing of the disease. So the very first graph here is showing you the total vaccination, and you can see the total vaccination behavior is preferred. So the total vaccination over the time is increased, and we started with 4,200, but we came up around more than 7,000. And the total susceptibles are decreased. It means more of the people are immune for the with the vaccination and recovered in this case. And this graph is the media effect. I plotted the media effect over the time, and you see the media effect increases when the peak is approaching. And it's at the peak when your media effect is at the peak, when your infection is at the peak. And slowly it in the newspapers or articles or on radio or TV in those days when there is a peak or the wave which is at the top, but it slowly goes down over the time. So here is the summary of our work. From simple assumptions, we can make models that might be simple or might be complicated. It depends on you. You can make the model complicated. I have shown you the example of a very complicated model, which is not easy to handle, or it's not easy to analyze mathematically. You can do it theoretically, but it's not that easy. Then mathematical models like a map making. You always make a map, your road map. What are your inputs? What are you trying to find from them? We need to decide which factors are important and which we can safely ignore. Means you have to make some assumptions for your model according to the real life. It's not like make the assumptions and then your results are not matching with your biological factors. You have to be very careful while making assumptions that your factors must match with your biological factors or the real life factors. And then in the end, we can say that all models are wrong, but some are useful. So you can always say that this model is wrong. You can bring up with some new interventions in that model, or you can improve those model according to your own thinkings. Because this is research and we can find this every time happening in the research. So thank you for listening, and now we are open to the questions.
Thank you, Dr. Safia, for this interesting presentation. And I'm so happy to be with you on this presentation today. So we are opening the questions for the audience, and I think I will start with. I think there is a question from Dr. Haider, the chair of math department. Can you hear me, Dr. Haider? Yeah.
Yes, yes, Dr. Ahmed. Thank you.
Hi, Doctor. Go ahead with your question.
I would like to thank Dr. Safia for her participation in our department today. Also, I thank Dr. Ahmed. Dr. Safia, my question is, in your opinion, in which real space the SIR models are defined? Is it in Banach space or Hilbert space? And thank you.
Okay. Since we are dealing with the population mostly in the infectious disease model, so our solution must be real, the numbers. So basically, the space you used here is a real space, and you know that real space is a Hilbert space also. So we can easily say that our ODEs are in real space and Hilbert space, definitely. Because I worked with a projected dynamical system in my thesis, and we worked there with a Hilbert space. And most of the models are infectious disease models. So we are very careful about that it should follow the Hilbert space properties in that model.
Perfect.
I hope I answer your question.
Thank you.
Yeah.
Thank you.
Thank you.
Thank you, Dr. Haider. We have also Dr. Zainab, Zainab Shahab. Can you hear me, Doctor? Yeah.
Assalamu alaikum, Dr. Ahmed and Dr. Safia.
Hi, salam. Alaikum salam.
First, it's a great opportunity for me and for the others to meet you here via Zoom from here to Canada.
Thank you.
And second, I would like to thank you for this interesting talk in disease model, SIR. Also, I want to thank you for the great explanation where you've tried to explain any simple things, in particular an SIR model. However, I have an inquiry and one question to Dr. Ahmed. First, it's for you, Dr. Safia, if you hear me.
Yeah, I'm
At the beginning Yes, at the beginning of your talk, you talked about the duration of the flu. Actually, I disagree with you on this point because nowadays, or where I've been in England, the duration of the flu took around 2 weeks. For this reason, nowadays, the doctor try to split between COVID-19 and the flu. For this reason, they ask the infected people to go to hospital to check if it's COVID or flu. And in your talk, you said
you're right.
it's around 8 or 1 week. So actually, I disagree with you on this point only.
Okay.
Yeah,
Okay.
it could be possible.
Okay.
Yeah,
Good
I
point.
agree with you. Means it's always
Good
changing.
point, Dr. Zainab. Good point.
It depends on the strains of the flu working at that particular season. Mostly
Yeah.
the researchers agreed on the 5 to 8 days for a simple H1N1 flu, but it depends on the strain which is working right now. The COVID and the strain, we don't know about the which strain of the flu is working right now. So you can safely say that it could go to 2 weeks, and it also depends on the human body also. Like maybe I can recover in 14 days, but some other person can recover in 5 days. Means how strong your immune system is. It depends also on that. Like we need to check some in-house modeling for that particular time period, that how it works. I agree with you, definitely.
Yeah. Okay. So thank you for you, Dr. Safia.
You're welcome.
And I have one question for you, Dr. Ahmed.
Oh yeah, cool. Yeah. Go
You
ahead.
in your slides, your players are human,
Yeah.
right?
Yeah. Yeah.
So are there another examples in which the players are not human? Thank you.
Oh yeah, thank you, thank you, Dr. Zainab. Yes, actually, we discussed the basic definition of the game here, where usually we predict that the players are human, which is the only human can make rational decisions. But there is some cases, or there is some special cases in games where the players are not human, which is usually used in a predator prey system. As I showed in one of my slides, there is a game of hawks and doves game where the hawks eats the doves. So in this kind of games, it's called evolutionary games, where the players are actually designed to choose a specific strategy without any thinking. So when the hawk try to eat the dove, the best strategy then can just do it. It's to run away, which is the strategy of saving life. This kind of exactly what you said is actually known as evolutionary games. And there is there is a lot of theory about this these games. Is specifically the mathematical theories about it. Yeah.
But the life it's more valuable, right?
Yeah.
So in your opinion, who will win in this game?
There is no winners and losers here. And it's actually, this game is played to explain how the environment is working in the world. So this
but we talked but you talked about two animals. One of them is very strong to eat the other. So so you
this
need
game
in your model to put something, I think, to say who will win or not. The meaning of win, I mean who will die or who will still alive.
Yeah, no. So this kind of games actually is played here or designed here to analyze the behavior of one population on another. So the population of the predator is trying or eating the population of prey. So in order to see how it goes between these populations, which is also known, just like SIR model, is known the predator-prey model. So in order to predict the behavior or analyzing these behaviors of the population is depending on how this this game is explained.
But sometimes the percentage of the weak animal,
yeah,
it's more than percentage of the strong animal, because the weak animal can run.
Yeah,
What do you think?
No, Dr. Zainab, we are actually trying here to not saving the life of one animal against the other. No,
But
we
this is
know
the game. This is the game you talked about.
Yeah, this game
of life. In my opinion, it's game of life.
No. This kind of games is actually we are trying to in this perspective. Our perspective with Dr. Safia is trying to see how if there is any infection goes inside the prey or the inside the prey, and there is the predator comes to eat the prey, and then the infection goes for everyone, and it makes distinctions to the both population. And we are actually here interested in saving the environment and the life. So we are not preventing the predator from eating the prey, because this is how the lives go on. The strong animal eats the weak animal, but we are trying to save the life of these both population in the environment, and we to make it safe, because sometimes in this kind of games the infection goes to the human being. So we are analyzing from this perspective, analyzing this game from this kind of perspective.
Okay, thank you very much for you, Dr. Ahmed, and for Dr. Safia. Hope to see you again, Dr. Safia, via Zoom here in Baghdad. Thank you very much.
Yeah, I want to add to Ahmed's question, because you are asking about whether the prey is dominating or the predators are dominating. Basically, this game is Nash equilibrium. So it's like a zero-sum game. Though, so nobody is in the situation of we are either reducing the prey or predator. But the problem is if one of the species infected, it can infect all others. So I think the Dr. Ahmed's work is on control theory. How can we control the infection at that particular disease, which is spreading either in predator or prey? So, and the other thing I want to mention, because he mentioned that this is SIR model. And since this is SIR model, so the population is conserved. If there is dying out, there is an increase of the population is still coming. The inflow and outflow are equal. That's the reason. So it's not like killing some of the animal, or obviously life is important. It's just like the cycle going on at its own, and we are just trying to vaccinate to reduce the infection. I hope it clears the things.
Yeah, thank you so much for this explanation. Thank you.
You're welcome.
So we have another question here from Dr. Ahmed Bakhit.
Okay.
Hi, Dr. Ahmed.
Assalamu alaikum.
Alaikum salam.
First, I would like to thank you for this amazing presentation. My question is, what is the difference between the concept of Nash equilibrium and the concept of ESS? Thank you.
If you allow me, I will answer this question,
Yeah,
Dr. Ahmed.
please go ahead.
Yeah. So in Nash equilibrium, actually, we are trying to solve the game where everyone is happy about their outcome. All the players will get happy about the outcome, because if they change their mind and use another different strategy, will not be good for them. So this, we call it a Nash equilibrium. But in ESS, we are actually, which in ESS we're calling the evaluationary stable strategy. So in ESS, actually, we are trying to see that this strategy is the best strategy over time. There is no other strategy can compete with this. So that means that it has to be Nash equilibrium, but it has to be survive strategy for over time. Is that clear, Dr. Ahmed?
Thank you. Yes.
Okay.
Thank you.
Perfect. Thanks.
Dr. Ahmed.
Oh, hi, Dr. Qasim.
Yes.
Go ahead, Dr. Qasim. Hi.
First of all, I would like to thank Dr. Safia and Dr. Ahmed for this nice presentation, but I have this question. Dr. Safia, in disease modeling, there are different kind of SIR model, such as SEIR,
right,
IVR, SI, and so on.
right.
In your opinion, how we know the best version of this different kind to use in such module?
Okay, you know, it depends on your inputs and outputs, what you want to study in that particular model or particular disease. You can expand the compartments according to your own choices. Like as I showed you in my recent work, that I have subdivided my compartments according to my own needs. And in another work, which I'm doing on a theme park with the COVID, the theme park is the Disneyland in US, and we want to check how the infection increases in that particular park with the visitors and the workers coming in and out of that. That's a meta population project basically, and in that model we introduce another compartments with asymptomatic and symptomatic infection, because COVID, you have heard about that, there are many cases where you don't show any symptoms, so you want to count them also in the disease. So it's not always according to some like a fixed model you have to use. You can expand according to your own outputs or whatever the results you are studying, you want to study, or your assumptions. So you always can expand. SIR is the basic model given from the start, but it's not like hard and fast rule that we have to follow SINR. We can add the compartments according to our own requirement. I hope I answer your question, Dr. Qasim.
Yes, Doctor. So that means depend on the parameter of the parameter in the modeling. We can choose.
Yeah, definitely. Means right now I'm working on a nursing home project, and my model is to study how the workers and the resident of the nursing homes, means the worker and visitor coming to the nursing home in Canada, is increasing the COVID exposure for the residents living there. And for that particular model, I have like 28 parameters to handle. And it's not that easy to find all those parameters from the data available. So you can increase your equations, your model, you can make it as much complicated as you want according to what you want to study. So it's up to you. You want it more simple? Simple means it's just like understanding, and complexity gives you the predictions from the model. I hope you got my point.
Thank you. Thank you for this nice talking in Department of Mathematics, College of Science, Mustansiriyah University. Thank you. Thank you.
Thank you, Dr. Qasim. Thank you. Just a quick note for the audience. I just put the link of the registration, sorry, in the chat. You can anyone can see it. Please just separate this link between all the participants. Is there any question? Further question? I'm just searching in the chat. There was a question, but I'm trying to get this question from Mr. Jamal or Dr. Jamal. I'm trying to see what is the question in just a second. Dr. I'm sorry, I can't get it.
Yeah, I found a question from Al Badrin. I think Ben Al. I'm sorry for my pronunciation of the Arabic name. I'm very sorry. Some person is asking about the quotes. Are you
COVID,
asking
yeah.
quotes from my side or from Dr.
Whatever,
Ahmed?
whatever. Just no. He's
Uh,
talking about COVID, so I think he's talking about SIR. I think he's
okay. The
Mr. Jamal.
Okay. The codes are available, means for the SIR model, it's simple. You can find it from the Google. But if I'm talking about my own work right now, it's not yet published. It's still in process. So I will share the codes once it's published. Definitely, I can share the codes.
Yeah. So also, I think it's Dr. Jamal. He's saying game theory works in COVID with perspective of social distance or not. Payoff can be designed accordingly. Is that
No,
right?
sorry. No, I answered this question. This is my answer. Jamal asked about the COVID, that the payoffs wouldn't be equivalent to the enriching their lives. If he's talking about the doctors who are helping us for the life care.
Okay.
And according to him, the game theory cannot explain the human behavior here. I want to have already answered, but I want to explain to all the audience that in that case, the game theory works in a different way. The game theory is not like killing someone and rewarding someone. Basically, we change the payoffs according to the situations. Like in the COVID situations, uh, I say if I involve the game theory, I will look for the social distancing because there is no vaccination right now, and all the people wearing the mask and those who are not wearing the mask. We have seen there's a lot of things going on for anti-mask movement. So if you're not wearing the mask, your payoff will affect the others. Means you are happy with the breathing and you want to enjoy, but your payoff will be the negative payoff for me. Because if I'm not immune, or I have the comorbidities like some special health conditions, heart problem, diabetics, or any other condition, it will harmful for me to get those germs, and in that case that payoff is negative payoff for me. So the game theory depends on what strategies we are developing and how we are taking them. It's for the doctors. I know for the doctors who are saving the lives are doing a great job. So if we want to develop some model where we want to see how we can affect the doctors at that particular situation, I say that the patients, or all those patients who are going to the hospitals, it's their responsibility to save themselves by wearing masks and the social distancing. But we have to observe here in Canada, we are not allowed to go to the walk-in clinics these days. We have to take the appointment. So there is no gathering. We can maintain the social distancing, and the doctors are easy and they can do their jobs also. So this kind of behavior could be studied by using the game theory. So game theory is basically not like life or death, but it's basically studying the behavior of the population according to their strategies, what strategies they are going to use in their daily life. I hope I answered the question in detail.
Yes, hopefully there is no complaints for now.
Very good.
Is there any other question from the audience? Now I'm trying to finish our talk with a great thank for my colleague Dr. Safia, and we are actually all the department of mathematical sciences here are happy of having you as a guest, and we ask you to do multiple workshop with us, or another talks in the future if you want, and then we open a lot. This talk actually in name of Dr. Haidar, Prof Haidar Ali. He's talking to me before today, and then actually before we getting to the workshop, he told me he want to continue our collaboration with you in the future. We can talk a lot, and we are very happy to have you on this platform here today again. And thank you for your time and for everything. And also, I want to thank all the audience today for their patience and their questions and their participants.
Yeah,
Thank you very much.
I want to add that I will be more than happy to discuss more about the infectious disease modeling with all of you. And it's very healthy discussion. I learn a lot with you also. So I'm open anytime, according to my schedule, because we are in the morning and you are in the night. That's the problem only. Otherwise, I'm good. We can talk more. This time is short, so we can't talk more about the infectious disease modeling, the stability and equilibria and everything. But we can do in future if there is another chances. Thank you all of you, and thank you for inviting me to have this talk. It's nice to meet all of you. Thank you all.
Very much. Thank you very much, Dr. Safia.
Yeah, take
Bye
care
for now.
and stay safe. Bye.
Assalamu alaikum.
Walaikum assalam.